Welcome everyone to today's Opixs training. My name is Markus Rignat. I'm a technical sales engineer at Fluxim AG. Opixs is Fluxim's latest simulation software for innovative display concepts. The idea behind Opixs is that user can analyze images based on their subpixel information such as pixel layout, JVL data, and CIE color points, and then get detailed statistic results such as a power heat map or the pixel distribution in chromaticity plots. Furthermore, Opixs calculates the power consumption and allows to compare different subpixel designs. With this, I'm at the Opixs live demo. In the Opixs live demo, I will show you 3 different pixel layout concepts, starting with a very standard RGB, red, green, blue concept, where a white LED is used for all subpixels, and on top are different color filters. Then I will go to a more advanced one where a fourth subpixel is added to the layout, and then the display is choosing 3 subpixels out of 4 to produce the color of the pixel. A third one is a more recent, more complex, advanced concept called TurboLED. There it's a tandem stacked concept where a dark and a light pixel is stacked on top of each other. All these 3 concepts I will simulate, and I will look at the power consumption. And as an example, I take this photo here. Okay, so let me switch to the simulation software. In the simulation software, we see here the GUI, and we see on the left side here the 3 already prepared examples. Let's start with the RGB example. There we can see here in the middle, I prepared already the 3 pixels. Each pixel I gave before a relative subpixel area, the CIE color coordinates, and in the JVL curves manager, I added the current density, voltage, and the luminance data for this pixel. The same I did for the green and the blue. And when we are looking at the chromaticity plot here on the right, we see the CIE color coordinates of our 3 subpixels. And here in this tab, we can see the imported JVL data. Here, the luminance over the voltage plotted. Then in the next step, we need to load the image. This we can do here in this tab. We can select an image. We can set a reference, luminance of white value. Here in this case, I put 1000 nits for the luminance of white. And furthermore, we can choose the color space out of a list of standard color spaces. Okay, all these things done, we can now would go to press here this button, run simulation. As I did it before, I can skip it and go directly to the results. In the results tab, we see here in the list the different subpixel combinations. In our case, in the basic one, where we only have 3 subpixels, there are not so many combinations, just the RGB. We see that in this RGB combination, most of the pixels are, except some black pixels. And then in this column here, the power consumption, power density was calculated for all this for all these pixels. On the right, we can have some illustrations like the heat maps I mentioned before. We can plot here the power density, the luminance, the current density, or the voltage, and have a look where in this image the highest luminance or the highest power was used. We can have a look also on the emissive pixels to see where these black pixels are. Here we see it with these little black dots. They are black, so there is no power needed as they are pixel is switched off. The chromaticity plot, we see the distribution of all pixels where they're laying in the color space. And in the power histogram, we see the distribution of the power over all the pixels analyzed of the image. So with this, the important number here is this power density. Now we go back to the next subpixel layout, is the RGB wide. When we go back where we set it up, we see here I set it up a fourth subpixel. So now Opixs is looking for the best combination of 3 subpixels out of these 4 subpixels when he analyzes this picture. And I forgot to mention, so for this fourth white subpixel, I added, of course, the color coordinates, and I imported the JVL data. Okay, so now we go to the result tab, as I did already the simulation before, and here we see the different combination what Opixs gave us. So when we look at the chromaticity plot, we can have a look which combination of 3 out of 4 subpixels Opixs used to calculate the color. And we see that these both combinations were used most, and in total it gave us a power consumption of 29 watts per square meter, so much lower than in the other one. To compare it directly, we can simply select both, and we see here the RGB power density consumption per display area is shown here. It's 105 watts per square meter. And with introducing this additional force white subpixel, the overall power consumption for this image is strongly reduced to only 29 watts per square meter. So now let me show you the TurboLED subpixel layout. This is a much more complex one, but it's also possible to do in Opixs. There we use stacked subpixels shown here. Here we can use it here, add a stack to pixel structure. And I did it, and I defined so a stacked subpixel with a deep and a light pixel. And in the chromaticity plot, you can see also the deep red and the light red color coordinates. Here is for the green stacked pixel, and here are the light and the dark blue pixel for the stacked blue one. Then I loaded for all 6 different subpixels, the JVL data, and I kept the same image. And when we are looking at the result, then we get a lot more combination. Opixs is calculating and looking which is the best option and to save the most power when displaying this image. And we can see here nicely in this chromaticity plot that when using the blue light, the green light, and the red light, we can display in this image nearly all pixel colors. And when we're looking at the heat map, we see also here clearly on the scale that we are much lower compared to the other two subpixel layouts. If we want to have a direct comparison, Opixs, we simply can select all three of them, and we are having directly the comparison of power density per display area here shown. This I showed you before, the RGB to RGB white, and with this turbo OLED subpixel layout, we even can reduce the power density per display area. With this, I'm at the end of the live demo. I switch back to the PowerPoint presentation where I would like to show you some more pixel layouts, which we also had a look at. So there I showed you simply this RGB side by side. Then there is also the normal tandem RGB, but we can also look at our RGB vertically stacked one with Opixs and how is the power consumption on with this sub layout. And when you're interested, I highly recommend to visit Fluxim's research blog. Here's the link. And with this, I'm at the end. So I thank you for your attention. And if you have questions, do not hesitate to write me an email. Okay. Thank you. See you. Bye.